Hi guys, let's take a look at your homework questions from 1.5. So most of this stuff is working with limits that either go to infinity or limits at infinity or limits where there's vertical asymptotes or things like that. So the first one we had multiple requests for was 37, and then we also had 45, and I think there were two people that wanted 47, so maybe we'll look at that one too. So for 37, we're being asked to find the limit here. We're going to -3 from the left of this guy. I imagine it's probably going to be 0 over 0, but let's plug in just like before, just like with normal limits, just to see what happens first. So let's see, we've got x squared plus 2x minus 3 on top, and on bottom we've got x squared plus x minus 6. If we plug in -3 and forget about the little negative here, we're going to get 9 minus 6 minus 3, which looks like 0 on the top, and on the bottom we're going to get 9 minus 3 minus 6, which is 0 on the bottom, so it's going to be indeterminate. All right, so one thing we can try and do here is factor the top and the bottom, and maybe something will cancel. So the top here will factor into x plus 3 and x minus 1, and the bottom here will factor into x plus 3 and x minus 2, I think. And then these guys are going to cancel out. All right, so that should give us a whole at -3. So if it's a whole and we wanted the limit as we go to -3 from the left, we can just plug in -3 with what's left. All right, because the left side and the right side should both go to the exact same value, and it's just the value of that whole. If it was an asymptote, then we'd have to check and see, is it going to infinity or whatnot. But if it's a whole, we just plug in after we cancel, and we're going to get -3 minus 1 on top and -3 minus 2 on the bottom. So that's -4 over -5, or 4/5, or 0.8. That would work too. All right, so there's that guy. I keep looking back and ask, did I factor this right? I think I did. I think it was just that easy. All right. So 45. I know you guys don't like trig, so yep, naturally we ask the ones that have the trig. So we're taking the limit as x goes to pi of the square root of x over cosecant of x. All right, so we don't like cosecant. It's not one of the trig functions we're good at, so let's change it. All right, it'll be the square root of x, and cosecant is 1 over sine of x. Well, if we're dividing by a fraction, we flip and multiply, so we end up with getting just the square root of x times sine of x with no fraction. And now it's the same function. Right, this is the same thing as what we started with. We just plug in pi. If we plug in pi, we get the square root of pi times the sine of pi. And if you remember the sine of pi, if you remember your little graph of sine, here's pi right here. Sine of pi is 0. So we get 0 times the square root of pi, which is just 0. And for 47, we've got the limit as x goes to 1/2 of x times the secant of pi x, like that. All right, again, secant's not one of the trig functions we like. We can change it to cosine, so this is going to be x times 1 over cosine of pi x. So this will be x over cosine of pi x, and we like that better. We understand what cosine looks like if we're plugging in 1/2 here. For x, on top we're getting 1/2. On the bottom, we're getting cosine of pi over 2. Take a quick little gander at the cosine graph. It looks like that. And at pi over 2, it is down there at 0. So if we have 1/2 on top and 0 on the bottom, that is an issue. All right, that is, from one side it's positive 0, the other side is -0. So for one side, like if it's a little bit less than 1/2, we're going to positive infinity. A little bit greater than 1/2, it's negative on the bottom, we're going to negative infinity. So this limit here does not exist. It's infinite. Well, it's negative infinity on one side, positive infinity on the other side, two different things, so we say it does not exist. All right. 52 was next. All right, so for 52, use a graphing utility to graph the function and determine the one-sided limit. We want the function is secant of pi x over 6. So we're going to rewrite this guy as, well, we don't have secant in our calculator, so we'd write this as 1 over cosine of pi x over 6. And then we type that in. And then we see what happens at 3 from the right. So we want a little bit bigger than 3. All right, so I got this ready ahead of time. Here it is on. Go to y equals. There it is typed in. 1 over cosine of pi x over 6. And we can zoom trig. Zoom number 7 for trig graphs. And it's going to graph it for us. It is a bunch of guys with, there's a vertical asymptote right here. Here's another vertical asymptote right here. I imagine this is the one that's at 3. If we want to be sure that there's a vertical asymptote there, we can go to table and we can see at 3, yep, there's an error. There's a vertical asymptote. So it looks like on the little bit less than 3, we're going up. A little bit greater than 3, we're going down. But let's just go back to our graph and look to be sure. So this right here is where 3 is. So a little bit bigger than 3. Actually, I guess the little mark here is pi, but 3 would be like right here. So it looks like we're going down here towards negative infinity. So this limit as x goes to 3 from the right of secant of pi x over 6, or 1 over cosine of that, equals negative infinity. It is going towards negative infinity because it's got a vertical asymptote there, and it's going down. Like it's this part of the graph. All right, so going down, vertical asymptote, negative infinity. All right, so that was 52. We don't have any questions here. Next we had was 88. So the graph shows the temperature T in degrees Fahrenheit of an apple pie T seconds after it is removed from an oven and placed on a cooling rack. So we take it from an oven, looks like it's 425 degrees in the oven at the start. So when it says find the limit as T goes to 0 from the right, what does that represent? Well, that limit is our starting temperature. So that is 425, and I'm assuming this is degrees, yep, degrees Fahrenheit. And that's the temperature of the pie coming out of the oven. Which I would assume is also probably the oven temperature. You probably set the temperature to 425. The apple pie got up to that temperature when it was cooking, or very close to it. All right, next we look at the limit as we go towards infinity. And we have this little dotted line here. So this is our horizontal asymptote here. And that's what the temperature is as it goes to infinity, which 72 degrees is probably the room temperature. Like the lowest it's going to go is the temperature of the surrounding area. So this is, we could say, is the temperature of the pie's surroundings after taken out of the oven. All right, so when we take our pie out of the oven, we're going to sit it out on the counter or something, and the temperature in our house, I guess, where we've been baking our pie is 72 degrees. That's the lowest it could possibly cool down to. Like if the room temperature is only 72 degrees, the pie cannot cool to less than 72 degrees. We'd have to put it in the refrigerator or something after that. So that's 88. 89, let's see, the table shows the world record times for running 1 mile, where T represents the year, T equals 0 corresponds to 1900, Y is the time in minutes and seconds, so we've got, this would be like 1923, 1933, 1945, 1954, here's Roger Bannister going under 4-minute mile right there, and so on all the way to 1999. If we went farther, like this would be 121, I guess would be this year. I don't know what the mile time was this year, but I think it was pretty close to 340. All right, so a model for this data is this function right here. All right, so there's our function that does this data, or very close to it, where the seconds have been changed to decimal parts of a minute. So we've changed these to decimals. So this wouldn't be 3 minutes and 43 seconds. This would be 3 point something. Use a graphing utility to plot the data and graph the model. Does there appear to be a limiting time for the 1 minute run? 1 mile. All right, so we'll go back to our calculator. I already typed it in, so let's just highlight this guy to make him show up. And let's just zoom regular here, zoom 6. It's not going to show us much. We probably need to go out to past 99. And yeah, it's not really showing up. There it is. Okay. All right, so let's see, make sure I've got it right. That minus that. Yep, that looks right. All right, so let's see, our window, we start at year 23, and we want to go probably into the future at least, so maybe 200 years. And our X scale, if we're going to 200, maybe we'll count by 10. Our minimum, we don't have negative time, so we don't need to worry about that. Our maximum, looks like our maximum is just over 4, so let's say 5. And now let's take a look at the graph of this guy. So here's our times. They're coming down. They're coming down. Coming down. Not sure if that's leveling off or not. Let's try to spread the window out a little farther. Let's maybe go 1,000 years and see what happens. Count by 100. All right, so we come down pretty quickly, and then it's getting longer and longer, the flat sections here, if you notice that. So look, my guess is there probably is. So use a graphing utility to plot the data and graph the model. So that's me graphing the model. There it is right there. Does there appear to be a limiting time for running 1 mile? Explain. It looks like there is. It looks like there will be a limiting time. And if we want, we could take the limit as x goes to infinity of 3.351 t squared plus 42.461 t minus 543.73, put the 0 there, I guess, all over t squared. All right, so what ends up happening here is everything that's less than the degree t squared, we're not going to care about because it's going to get canceled out. So like this guy is going to be infinitesimally small compared to this guy. Same with this minus 500. The only thing we're going to worry about is the highest power of t on top and bottom. So it's those two. And this only works when you're going to infinity that you can do this. All right, so this is essentially equal to 3.351 t squared over t squared as we go to infinity. I should probably write that. I should probably also use t as our variable and not x. All right. So if we look at this limit, the t squareds cancel out, and we get 3.351. So that right there is our answer, and that's in minutes, 3.351 minutes. A little bit faster than I can run the mile, but you know, I'm getting there. I'm getting there. So yes, there does appear to be a limit, and that's what it is because we took the limit. All right. Or you can say based on the graph, it looks like there's a horizontal asymptote. That would work too. All right, next up, we wanted 101, 102, and we had a couple people ask about 106. So let's take a look at those. So the first one, 101, as we go to infinity of e to the negative 2x, this would be e to the negative 2 times infinity. So this would be e to the negative infinity, which, I mean, you can either just know that goes to 0, or you can think of this as 1 over e to the infinity, which is like 2.7 times 2.7 times 2.7 times 2.7, an infinite number of times. So what ends up happening is this bottom is going to a pretty big infinity. The top is still 1. So that means the limit is going to 0 here. Right, going to 0 pretty quickly, actually. With number 102 here, let's see, we're going to infinity. We've got 2 to the infinity on top, and we have 2 times infinity on the bottom. And really the question here is, which is bigger, the top or the bottom? Well, it turns out exponentials are much bigger than just a linear function. So that means this guy right here is going to go to infinity. If you don't believe me, you can plug in some numbers and check. Let's just go to our calculator real quick, and let's just try 100, like 2 raised to the 100 divided by 2 times 100. All right, E27. So this is 6 with 27 zeros after it. It's a pretty big number, and this is only 100. All right, if we go a little bit bigger, like if we went to maybe 500, we're probably going to get an overflow error because it's going to be too big. Yeah, overflow, too big. All right, so it's getting really big really fast. I wonder if can I go to 200? Or is that going to be too big? It's probably going to be too big, but we'll try it. Oops, it jumped on me. I caught it. Yeah, so now we're raised to the 57. So as you can see, these numbers are getting real big when we're only in the hundreds, and we're going to infinity here. So that means this guy is going to infinity. He's just going to keep going up. You could also look at the graph and check out what happens there. That would also be helpful. All right, the last one here, 106. We're going to negative infinity, okay, of this guy. All right, well, if we, so we're going to have 2 times negative infinity squared. So this term is going to go to infinity. We're going to have minus 2 e to the negative infinity. This term is going to go to 0. We already saw e to the negative infinity goes to 0 from the first one here. All right, this one's going to go towards infinity. This one's going to go towards infinity. This term is also going to go to 0 because it's going to be e to the negative infinity, which we also saw already was 0. So really, again, when we're going towards infinity, we only want to look at the highest power on top and bottom. And since these guys are going to 0, they're not part of the highest power. The highest power or the highest degree term that we're looking at are those two as we go to infinity. This x is minuscule compared to this x squared here. So what we get here is that this is essentially equal to the limit as x goes to negative infinity of 2x squared over 4x squared, which the x squareds cancel. We get 2 over 4 or 1/2 as our answer. So this will have a horizontal asymptote as we go backwards toward negative infinity of y equals 1/2. So we have an HA y equals 1/2. And that's how we write horizontal asymptotes. We write y equals whatever the number is. All right. If we're going to positive infinity, which is not what the problem is, but the problem, if it did ask that, so like if we did redo 106, say 106b, if we wanted the limit as x went to positive infinity of that guy, of 2x squared minus 2e to the x over 4x squared plus x minus 3e to the x, then the only terms that we would actually need to look at are these two, because these guys are so much bigger than all the rest of those. So we would say that this is essentially equal to the limit as x goes to infinity of negative 2 e to the x over minus 3 e to the x. The e's are going to cancel out, and the negatives are going to cancel out. We get 2/3. So we're going to get a horizontal asymptote of y equals 2/3 as x goes to infinity, and this one was as x goes to negative infinity, like that. So that's how we can differentiate which horizontal asymptote is which. We'll go over more ways to do this later. We'll use something called L'Hopital's rule. And it will actually be easier, but, well, maybe not. Who knows? But we will go over that later. All right, so that is it for homework questions. So make sure you get your review done, ready for the test.